The goal of this problem is to look at how to calculate the pH for a sodium formate solution. Some of the information provided is we have the Lewis structure for sodium formate. It consists of a sodium ion with the formate anion, and I've also provided the Ka for formic acid, which is 1.8 times 10 to the minus fourth. Just for trivia purposes, formic acid is what's in bee stings that causes the itchy pain and the swelling attributed to those stings. For this problem, what I thought we could first do is try to predict whether we expect the pH to be less than 7, greater than 7, or equal to 7. If we look at the sodium formate cation, it'd be sodium and formate, and we can synthesize sodium formate by a reaction of sodium hydroxide with formic acid. We know that sodium hydroxide is a very strong base, and we know that formic acid is a weak acid. And because formic acid is a weak acid, we can deduce that formate, which is produced during the dissociation of formic acid, is a stronger base than water. Recall all weak acids have this property, in which the conjugate base produced is a stronger base than water. Therefore, it's not as thermodynamically favored to produce formate. Given that formate is a stronger base than water, we can deduce that formate will generate hydroxide ions in solution. Given that hydroxide ions are generated in solution, we would predict that the pH would be greater than 7. This is also supported by the fact that if we have a strong base reacting, it produces a non-hydrolytic conjugate. Therefore, sodium cation is non-hydrolytic, meaning it does not undergo an acid-base reaction with water. Therefore, because formate is the only thing that reacts with water, and because formate is a stronger base than water, we know that formate will generate hydroxide ions in an aqueous solution. The next step is we know that Ka for formate is 1.8, formic acid, is 1.8 times 10 to the minus fourth. We can use our expression that we derived in class Ka times Kb equals Kw to determine the conjugate base Kb value. We would just say Kw divided by Ka, and we're assuming room temp, and that will be true for almost all of these equilibrium problems. Therefore, we can just use the constant 1.0 times 10 to the minus 14th unless otherwise specified. And I divide this by 1.8 times 10 to the minus fourth, and we get 5.5 times 10 to the minus 11th. Therefore, formate is a fairly weak base. The pH should not be much greater than 7. It will be greater than 7, but it's a fairly weak base. All right, what we can do is I'm going to write the expression for sodium formate reacts in water to generate formic acid. and sodium hydroxide. We would have the associated proton transfer as shown. Initially, we have a 0.1 molar solution of formic acid, and I'll say 0 and 0 for sodium hydroxide and formic acid respectively, the conjugate acid and the conjugate base, the products. Therefore, this will decrease. Equilibrium will proceed from left to right to generate product. And we get this expression. The last step is simply to set up a Kb value. We know that Kb would equal the hydroxide ion concentration times formic acid. I'm going to use Fa to represent formic acid, divided by the sodium formate concentration. If we look at the value for Kb, this is 0.1, and this is 10 to the minus 11th. We have a very large difference between the concentration and the Kb value. Therefore, what I'm going to assume, given it's at least 1,000 times difference, is this value is approximately 0.1. In other words, the amount of dissociation for sodium formate will be negligible, given the very small Kb value compared to the concentration. It's 10 to the 10 times different. Therefore, we can assume negligible dissociation. Okay, so therefore at equilibrium we have X and X. Notice, given it's 1 to 1 to 1, we have the same concentration of formic acid and sodium hydroxide at equilibrium. And this value is 0.1. We're assuming that it's roughly 0.1 instead of 0.1 minus X because of the negligible dissociation. So what I can do is I can rationalize that X, which is equal to a hydroxide ion concentration, is simply the square root of Kb times 0.1. If we look at the numerator, this would be X times X, or X squared. This would be X squared equals Kb times 0.1. Hence, X, which is equal to the hydroxide ion concentration, is equal to Kb times 0.1. So Kb times 0.1, or Kb times the base concentration, taking the square root of that product will give us the hydroxide ion concentration for a sufficiently dilute base. And if we calculate the pOH, so the negative log of the resulting value, we get the pOH is equal to 5.6. And we know that pH is equal to 14 minus pOH, or in this case the pH is 8.4. And this matches our original assumption that the pH should be greater than 7 or slightly basic. Therefore, a 0.1 molar solution of sodium formate has a pH of 8.4. And to recap, a key equation is the hydroxide ion concentration is equal to Kb times the initial base concentration. And I'm going to use an approximate sign to emphasize the fact that it's not exactly equal, but it will be close enough. And just a final point, we can do the same with the hydronium or hydrogen ion concentration with regard to Ka and the initial acid concentration. And we know that pH plus pOH equals 14 from the autoionization of water.